Hello friends, welcome you all to the 34th lecture on function analysis and its applications. In this lecture, we will discuss the orthogonality of vectors. Content of today's lecture, orthogonality of vectors. Definition of the orthogonality of vectors. Let H be a Hilbert space, then xy belonging to H are said to be orthogonal, denoted by x perpendicular y. This is the notation of perpendicular. If inner product of xy is equal to 0. The vectors xy belonging to H are said to be perpendicular if inner product of xy is equal to 0. From this definition, we have the following consequences. First, the relation of orthogonality is symmetric. That is x perpendicular y if and only if y perpendicular x. Explanation. X perpendicular y, it means inner product of xy is equal to 0. Taking the conjugate complex of both sides, then inner product of the xy bar equal to 0. 0 bar is 0. Okay. Conjugate complex of the inner product of xy is inner product of yx. This is already 0. So, inner product of yx is equal to 0. It means y perpendicular x. So, if x perpendicular y, so we can say that y perpendicular to x. Second, if x perpendicular y, then alpha x perpendicular y for every scalar alpha belonging to C. Explanation. Since x perpendicular y, it means inner product of xy is equal to 0. So, if we multiply the any scalar of this equation, so we can write alpha inner product of xy, and this can be written as inner product of alpha xy. Okay, this is equal to 0. That is inner product of alpha xy equal to alpha into inner product of xy. Inner product of xy equal to 0. That is alpha into 0 is equal to 0. Inner product of alpha xy is equal to 0. It means alpha x is perpendicular to y. So, alpha x perpendicular y. Third, since inner product of 0 x is equal to 0 or any x belonging to H, we have 0 perpendicular x for all x belonging to H. If x perpendicular x, then x must be 0. Explanation. If x perpendicular x, it means inner product of x is equal to 0. Inner product of x, that is norm of x square. That is norm of x square is equal to 0. This implies that x is equal to 0, because if norm x is equal to 0, if and only if x is equal to 0. Okay. So, if x perpendicular x, then x must be 0. Pythagorean theorem. If x and y are two orthogonal vectors in Hilbert space H, then square of the norm of x plus y equal to square of the norm of x minus y equal to norm of x square plus norm of y square. Okay, this is the Pythagorean theorem. Okay, we know that in right angle triangle, okay, suppose this is the vector x and this is the vector y. So, this is the vector x plus y. Okay. Similarly, corresponding the vector y. So, this is vector y. and corresponding to this is vector x. So this one, this is vector x plus y, okay, and this is y and this is x, okay. So what is the vector this? So this vector is, okay, this is vector x and this is vector y. So this is the vector x minus y. So diagonal x plus y and diagonal x minus y. For this triangle A, B, C, this is diagonal of xy, and triangle ADB. Okay, so diagonal is x minus y. Okay, so magnitude of this line and this line as norm x, magnitude of AB is norm x, magnitude of BC is norm y, and this is norm x, and this is norm of y, and diagonal BD is norm x minus y, and this norm of x plus y. Okay, so AC square is equal to AB square plus BC square. This is the Pythagorean theorem. Okay, so norm of x plus y square is equal to norm of x square plus norm of y square. Similarly, diagonal this, norm of x minus y square equal to norm of x square plus norm of y square. Okay, now we prove it. Since x perpendicular y, we have inner product of x, y is equal to 0. Okay, this vector and this. Now, a square of norm x plus y, we can write inner product of x plus y, x plus y. Okay, because norm of x square is equal to inner product of xx. So using the fourth property of inner product, this can be written as inner product of xx plus inner product of xy plus inner product of yx plus inner product of yy. Okay. Inner product of xx, that is norm of x square, and inner product of xy, since xy orthogonal vector, it means inner product of xy is equal to 0, and also inner product of yx is equal to 0, plus inner product of yy is norm of y square. Okay, so norm of x plus y square is equal to norm of x square plus norm of y square. Similarly, norm of x minus y square, that is square of norm of x minus y. This is also can be written as inner product of x minus y, x minus y. Using the first property of inner product, we have inner product of xx minus inner product of xy minus inner product of yx. This is minus minus plus, that is plus inner product of yy. Again, inner product of xx is norm of x square, inner product of xy is equal to 0, minus inner product of yx also 0, plus inner product of yy is norm of y square. So we have norm x minus y square is equal to norm of x square plus norm of y square. Hence proved. Generalization of Pythagorean theorem. If S is the set of x1, x2 and so on xn, is an orthogonal subset of a Hilbert space H, then norm of summation xi square, where I is equal to 1 to n, equal to summation I is equal to 1 to n norm of xi square. Okay. Proof is very simple. We have norm of summation xi square, where I is equal to 1 to n. Here, suppose as one vector, so this can be written as inner product of summation I is equal to 1 to n xi and summation j is equal to 1 to n xj. Okay. So we can write here I is equal to 1 to n xi, or we can write j is equal to 1 to n xj. There is no change. So this can be written as summation j is equal to 1 to n xj. Okay. So if we expand this up to n time, this is also up to n time. So we can write first term is as like term. Summation I is equal to 1 to n inner product of xi. Okay. And another term we can write. So if xi and xj both different, that is plus summation I is equal to 1 to n I j is equal to 1 to n inner product of xi xj. Okay, where I not equal to j. So this term is 0 because inner product of xi xj is 0. Okay, for xi not equal to xj. So first term we have summation I is equal to 1 to n inner product of xi. Okay. So inner product of x is norm of x square. So here summation I is equal to 1 to n inner product of xi can be written as summation I is equal to 1 to n norm xi square. So it is proved here. Next definition. A vector x is said to be orthogonal to a non-empty subset S of a Hilbert space H, denoted by x perpendicular S, if x perpendicular y for every y belonging to S. Two non-empty subsets S1 and S2 of a Hilbert space H are said to be orthogonal, denoted by S1 perpendicular S2 if x perpendicular y for every x belonging to S1 and y belonging to S2. Orthogonal complements. Let S be a non-empty subset of a Hilbert space H. The orthogonal complement of S denoted by S perpendicular. It is defined as S perpendicular equal to x is the element of H such that x perpendicular y for all y belonging to S. Okay. So S perpendicular, that is x is the element of H, y is the element of S. Okay. When x perpendicular y, that is inner product of x, y equal to 0. Thus, S perpendicular is the set of all those vectors in H which are orthogonal to every vector in S. Next theorem. If S is a non-empty subset of a Hilbert space H, then S perpendicular is a closed linear subspace of H and hence a Hilbert space. So proof. By definition of S perpendicular, we have S perpendicular is defined here. So S perpendicular equal to x is the element of H such that x perpendicular y for all y belonging to S. Meaning of this, x perpendicular y, that is inner product of x y is equal to 0. This, since inner product of 0 y equal to 0 for every y belonging to S, then at least 0 is the element of S perpendicular. Okay. Hence, S perpendicular is non-empty. Now let x1 and x2 belonging to S perpendicular and alpha beta be scalars. We have inner product of alpha x1 plus beta x2y equal to inner product of alpha x1y plus inner product of beta x2y as per the first property of inner product. Okay, again we are applying the third property of inner product, that is alpha inner product of x1y plus beta inner product of x2y. Okay, so here x1 and x2 belonging to S perpendicular, it means inner product of x1y is equal to 0 and inner product of x2y is equal to 0. That is inner product of alpha x1 plus beta x2y is equal to 0. This proves that alpha x1 plus beta x2 is the element of S perpendicular. Hence, S perpendicular is a subspace of H. Next, we show that S perpendicular is closed subspace of H. That is, we shall show that X is any limit point of S perpendicular. Let sequence xn belonging to S perpendicular and xn converges to X in H. Okay, we suppose here. Then we have to show that X is the element of S perpendicular. For this, we have to prove inner product of xy is equal to 0 for all y belonging to S. Since xn belonging to S perpendicular, it means inner product of xn y is equal to 0 for every y belonging to S, for n is equal to 1, 2, 3 and so on. Since the inner product is a continuous function, so we have inner product of xn y converges to inner product of xy as n tend to infinity. This can be written as inner product of xn y minus inner product of xy tend to 0. So applying the fourth property of inner product, we can write this inner product of xn minus xy as common. So inner product of this can be written as inner product of xn minus x y tend to 0 for all y belonging to S. So inner product of xn minus x y tend to 0, it means xn minus x tend to 0 as n tend to infinity. That is, this is right side, so xn converges to x. Here inner product of xn minus x y tend to 0 for all y belonging to S. It means x minus x is the element of S perpendicular. Okay, that is x n converges to x. Okay, thus x belonging to S perpendicular, hence S perpendicular is a closed subspace of H. Now S perpendicular is a closed subspace of the Hilbert space H. So S perpendicular is a complete space and hence it is a Hilbert space. Why this is S perpendicular is complete? Because S perpendicular is a closed subspace of the Hilbert space H. Hilbert space already complete space. Okay. So noting point, in this above theorem we have shown that S is non-empty subset of Hilbert space H, then S perpendicular is closed subspace of H. Since H is complete and every closed subset of complete metric space is complete, therefore S perpendicular is complete. Hence, with respect to the inner product on H, S perpendicular itself is a Hilbert space. This completes the proof of theorem. Next theorem, an orthogonal set of non-zero vectors is linearly independent. Let S is equal to x1, x2 and so on xn be an orthogonal set of non-zero vectors in Hilbert space H to prove S is linearly independent. Suppose summation I is equal to 1 to n ai xi is equal to 0, where ai are scalars, from which inner product of the summation I is equal to 1 to n ai xi xr equal to inner product of 0 and xr. Okay, because summation I is equal to 1 to n ai xi is 0. Okay, so this is inner product of 0 xr, that is 0. This implies that summation I is equal to 1 to n ai into inner product of xi xr is equal to 0. Okay, so this is very simple. So by assumption, inner product of xi xr is equal to 0 for all I except I is equal to r. Okay, because xi and x are different vectors. Okay, so inner product of xi xr is 0. But if I is equal to r, so ar into inner product of xr xr is equal to 0. This is defined. Okay, so this implies that ar is equal to 0 for all r is equal to 1, 2 and so on n. So equation 1, 0 and all ai is equal to 0, I is equal to 1 to n. So equation 1 declares that S is linearly independent. So more precise explanation we can see here. From equation 1, we have a1 x1 plus a2 x2 plus and so on an xn is equal to 0. Equation 2. To prove a1 is equal to a2 is equal to and so on an is equal to 0. Now multiplying equation 2 by x1. So we have a1 x1 into x1 plus a2 x2 into x1 plus and so on an xn into x1 is equal to 0 into x1. So here x1 x2 are different vectors, that is inner product all terms are 0 except first term. First term we have a1 into x1 square is equal to 0. So x1 is non-zero vector, it is here given. So a1 is equal to 0. Similarly, we multiply equation 2 by x2. We have a1 x1 into x2 plus a2 x2 into x2 plus and so on an xn into x2 is equal to 0 into x2. That is all terms are 0 except second. Okay, so we have a2 into x2 square is equal to 0. So x2 is non-zero vector. So we have a2 is equal to 0. So and so on, multiplying equation 2 by xn. So we have a1 x1 into xn plus a2 x2 into xn plus and so on an xn into xn is equal to 0 into xn. So all terms 0 except last term. So last term an xn square equal to 0. So xn is non-zero vector, an is equal to 0. So we see that each a1, a2 and so on an are 0. Okay, so that is ar is equal to 0 for all r is equal to 1, 2 and so on. So equation 1 is linearly independent. So equation 1 declares that S is linearly independent. Similarly, an orthonormal set of vectors is linearly independent. Proof is similar as above. Okay. Let S is equal to x1, x2 and so on xn be an orthonormal set in Hilbert space H to prove that S is linearly independent. Let summation I is equal to 1 to n ai xi is equal to 0, where ai are scalars. So inner product of summation I is equal to 1 to n ai xi xr equal to inner product of 0 XR, that is 0. Okay. So this can be written as 0. Okay. So this implies that summation I is equal to 1 to n ai inner product of xi xr is equal to 0, or ar into inner product of xr xr is equal to 0. Okay. So expanding this, so if xi and xr different vector, that is inner product of xi xr is 0. Okay. And if I is equal to r, so we have ai into xr xr. So we have one term or ar inner product of xr xr is equal to 0, that is rs term. Okay. So ar into 1 is equal to 0, that is ai is equal to 0 for all I. Hence S is linearly independent. So proof is similar as this theorem. Okay. In this lecture, we have discussed the orthogonality of vectors and related theorems. These are the references which have been used in this lecture. Function analysis, Dover publication, written by George Beckman and Lawrence Naressi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publisher, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.